Hello and welcome to Topic 7, Lesson 2, and I'm going to go over advanced Lewis structures. These are going to be examples of doing Lewis structures with things that are much more complicated than what we did in the first lesson. So we're going to talk about polyatomic ions in here and things that break the octet rule. So let's get started. I'm Mr. Rast, and I'll start you off on your journey here. So on the last lesson, and if you didn't see the last lesson, please go back and watch it. We talked about a different method of connecting Lewis dot structures, and I called it connect the dots. In these examples that we're going to be going over, the connect the dots wouldn't work straightforward. So there's one additional thing that I'm adding to the connect the dots rule, which is called the bank. So if we have the bank, and I'm just going to show you this, but I'll also go back and forth with the normal textbook way that you would solve this, so you can just ignore the connect the dots method if you don't want to. But if you do the connect the dots method, you need to have the bank to solve some of these. So you're going to need the bank to solve something like this. How would you do the Lewis dot structure for hydronium? So how you would do this is hydronium is H3O positive. So let's look at this. So we just said hydronium is H3O positive. By the way, this is the polyatomic ion that you find a lot of the concentration of this in water dissolved in water will make the solution more acidic. So this is the presence of hydronium is what makes things an acid. So the Lewis structure for hydronium, my professor, when I was talking in college as a teacher's assistant to some of the students, said that you can't do the connect dots thing, because what are you going to do about this? What are you going to do about, you can do Lewis dot structures for ions, so how would you do this? And so this is what kind of led us to the bank. So hydronium would consist of 3 hydrogens, and I'm going to put 1 valence electron on each hydrogen because hydrogen has 1 valence electron, and it consists of 1 oxygen. And oxygen has 6 valence electrons. And if you're not sure why I'm putting these dots where I'm putting them, go back into prior lessons, please. And it's explained clearly there. So anyways, I have this situation here, but also I've taken care of my 3 hydrogens right here, and I've taken care of my oxygen right here, but I've got a charge, a positive charge. And what does it mean when an ion has a positive charge? It means that it has lost an electron, it has more protons than electrons, so it's lost an electron. So I'm going to use a bank, and I'm going to put a box here. And this box is a reminder to me that something has to leave. I have to lose an electron. So when I'm all done, I have to have a dot in this box. So now I've got my setup. I've got my hydrogens, my oxygen, my charge. My charge is right here. That's reminding me I've got to put, by the way, if it was +2, I would put 2 boxes up here. That would mean I have to put 2 electrons in there. So I've got all this set up, and now I'm going to do my second step, which is connect the dots. Connect the dots. La, la, la. I've connected the dots, and there's nothing more to connect. This is all alone, and there's nothing more to connect. And by the way, this would just be H2O, but hydronium is H3O positive. So what am I going to do here? Well, now that I've connected everything I could, I'm going to look at this box and say, oh yeah, I have to add something to the box. So if I add an electron to the box, well, I have to. I could add 1 from the oxygens, or I could add 1 from the hydrogen. If I add 1 from the hydrogen, it's pretty much over. So that wouldn't be the electron. So let's add 1 from an oxygen. So I'm going to put an X through this one, and I'm going to put it up here. I got to keep track. I don't put an X through something without placing it somewhere else. So I put an X through it, place it over here, and now lo and behold, I can connect these dots. Now I have to write it clean. Remember, this whole thing here has a charge. This whole thing has a positive charge. So now I'm going to write this clean. And when I write ions clean, I use brackets to show the charge. But let's write it clean. I've got an oxygen, and on top of it, I've got a lone pair of electrons, the way I drew it. To the right, I have a hydrogen. To the left, I have a hydrogen. And below it, I have a hydrogen. And the whole thing has a positive charge. That's how you write a Lewis dot structure for an ion. You have to put brackets, not parentheses. Make sure you square them off, and you put the charge up there. So that would be hydronium using the connect the dots method. Let's take a look at the next one. let's do some examples. So we have hydronium. So now what would we do if it was a negative charge? And I'm going to use the bank to do something with a negative charge and see how that works out. So let's try this. How would I use the bank to do something with a negative charge? So I've got hydroxide here, hydroxide. So that is OH negative is hydroxide. I have an oxygen, which has 6 valence electrons, 1, 2, 3, 4, 5, 6. And I have a hydrogen, and that has 1 valence electron, and I have a negative charge. So that means I have an extra electron. I don't know where that extra electron is going to go right now, so what I'm going to do is I'm just going to, instead of putting a box, I'm just going to put a dot up here. This means I got to get rid of this dot. It's got to go into my polyatomic ion. If I have a box, that means I need to put an electron into it. If I just put a dot up there, I got to get rid of this one. So I've got this dot up here. And now I've taken care of my oxygen with my 6, I've taken care of my hydrogen with my 1, and I've taken care of my charge up here. If it was, again, if it was negative 2, I'd put 2 dots up here. If it was negative 3, 3 dots. Very good. So I connect the dots, connect everything together, and now I got to analyze what's going on here. Well, I've only got 1 dot here, and right now hydrogen has a helium configuration. It's got 2 electrons around it, so hydrogen's pretty good. Oxygen is not so good. It's got 1, 2, 3, 4, 5, 6, 7. It needs an extra electron. Well, maybe this is why hydroxide has a negative 1 charge, because it needs 1 more electron, and that extra electron can go over here and pair up. And now my oxygen has 8, followed the octet rule, and my hydrogen has 2. So this is perfect. Now let's write this clean, and remember this whole thing has a negative charge. So I'm going to write it nice and clean. That's my third step, is always to write it clean. And I'm going to use brackets, nice squared off brackets like that. So that would be the answer for hydroxide. Okay, we'll do another one. This one's going to be a little more challenging, actually a lot more challenging. This is chlorate, a great example of a challenging Lewis dot structure. And really, they don't get much harder than this one here. So see if you can follow along with me on this one. It's a good one to stay awake on. So chlorate. Chlorate is ClO3 negative. That's the polyatomic ion for chlorate. So chlorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. And I've got, that's my chlorine. I've got 3 oxygens, so I'm going to put 1, 2, 3 oxygens. And they all have 6 valence electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, and so I got my oxygens taken care of, and I've got an extra electron, so I'm going to put that one up in the bank. Well, I connect here, and now all of a sudden I'm done. Chlorine is, everything's connected. I can't do anything more with the chlorine, and things are very unstable, and I've got 1 extra electron to fix stuff. So it looks like a bad situation here. So you have to be quite creative. In a bank, you can make deposits and you can make withdrawals. So to do this, we're going to try to take a look at this and figure out how can we get everything connected and make sure everything follows an octet rule. So right now the chlorine, by doing the connect the dots method, I'll always keep 8 around my center atom as long as I make those bonds. So right now it's got 8. It's got 1, 2, 3, 4, 5, 6, 7, 8 around it. It's a good situation. So to keep that good situation and to connect to these other oxygens, I have to figure out a way to do that. And just as I can take out of the bank and I can add to the bank, during the course of one setup, I can add and I can go as many times with deposits and withdrawals. So take a look at this. I'm going to make a deposit to the bank. I'm going to cross out 1 and put another electron in the bank. By doing so, now I've got a spot for the chlorine to make a bond. And so if I bond here, now chlorine still has 8 around it. It's got 1, 2, 3, 4, 5, 6, 7, 8. So this method of using a bank will keep my octet working for my center atom here. But now I've got 2 in the bank. And still I haven't connected everything. The first priority is to get everything connected once. So if I did this here, maybe if you're starting to think right now logically, I could do this again here. So let's put another electron in the bank, and I can connect over here. Okay, Now good, the chlorine has 8 electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. My oxygens are deficient though, they have 7 around them. And so you might think, well, maybe I should start connecting the oxygens, or what could I do here? Don't forget, you got a bank here. You got to get rid of these 3 electrons. They are part of this polyatomic ion. So we have each one of these has only 7, and so if we give 1 to each of them, they'll have 8. So if I take 1 here, place it here. Now this oxygen's got 8. Place it here. This oxygen's got 8. Take 1 out of the bank, place it here. This oxygen's got 8. Remember, the whole thing has a negative charge. Let's write this nice and clean. O to oxygen to a chlorine to an oxygen to another oxygen, and this polyatomic ion has a negative charge. So that would be chlorate's electron configuration. Okay? It's good. Okay, so now let's take a look at some more challenging examples, and we're gonna look at boron trifluoride right now. Boron trifluoride. By the way, people that are very close to you, that you can share your most intimate thoughts with you, are often referred to as boron difluorides, which would be your BFF. Never mind. So, boron trifluoride. Let's take a look at this one. I'm going to go old school, not old school, but the textbook kind of way of doing this. How you would solve this is you take boron, which has 3 valence electrons, and you have 1 boron, so you've got 3 from the borons. You have 7 valence electrons for fluorine. You have 3 of them, so that's 21. The whole boron trifluoride, you're going to have 24 valence electrons to play around with. That's the first step. The second step is to connect everything with bonds. So we're going to use that center atom, which is boron, and we connect everything with bonds. And each bond counts as 2 electrons. They're sharing 2 electrons. So right now we have used up 1, 2, 3, 4, 5, 6. So from my 24, I used up 6 in these bonds right here. So that leaves me 18 electrons left over. And so the last thing you do with the normal textbook way of solving this is you start adding those electrons around the atoms so that everybody makes an octet. And so I'm starting to add them up, and I'm placing them all around. And I'm stopping at 16 because as I'm doing this, I'm starting to do this, I'm filling them up, and I've got 8 around this fluorine, 8 around this fluorine, and right now I've got 6 around this fluorine, and I've also got 6 around this bromine. So I might be tempted to put those 2 electrons here, but remember, the fluorine's deficient here. So those 2, if I'm following all my rules properly, would be shared between them. So I would have 1 double bond and 2 single bonds. That would be the textbook way of solving this. However, fluorine is much more electronegative than boron. It's very electronegative. Fluorine is located way over on the right side of the periodic table. It's the most electronegative element. Let's take a look at that. Fluorine is very electronegative. It is located, it's not focusing very well. Fluorine is located right over here. Boron is over here. So fluorine is very electronegative, meaning it doesn't want to share electrons. It wants to keep those electrons to itself. And boron is not as electronegative, so it doesn't get to hold on to them as much. And so in essence, what's going to happen is this double bond is not going to occur. This double bond is not going to occur because the fluorine is so electronegative. It's not going to share twice with the boron. It's going to hoard those electrons. Even though it could have a stable configuration, this is not what actually happens with boron trifluoride. Boron trifluoride actually forms like this. The actual electron configuration is like this. And if we did the connect the dots method, it's pretty straightforward how this turns out, because boron has 3 valence electrons, 1, 2, 3. Fluorine has 7, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And there's 3 fluorines, 1, 2, 3, 4, 5, 6, 7. And so I start connecting these dots here. And I can see, just by the connect the dots method, boron trifluoride, I kind of get this situation. I'm writing it clean because that's what I'm asking you guys to do, is write them clean. Okay, so I get this situation here of 3, and it just kind of naturally occurs when you do the connect the dots method. Especially if you're not thinking about double checking that you met the octet, you would just accidentally do this, but that actually accidentally doing this is, which is really cool, the correct answer. Note in this structure here that boron only has 6 valence electrons around it. It's only got the 1, 2, 3, 4, 5, 6 valence electrons around it. It doesn't have 8. Because it only has 6 valence electrons around it, boron trifluoride is what we would call electron deficient. The boron is electron deficient, and so this is a very reactive molecule. So by doing Lewis dot structures, you can learn something about the chemical properties of compounds. You do the Lewis dot structure and you take a look at here and you say, you know what, boron trifluoride is not a stable molecule. It's electron deficient, and because of the structure, because you understand the octet and you understand what you're doing and you build these things properly, just saying BF3 doesn't really let me know that it's unstable. But when I do the Lewis dot structure, I can see that it's unstable. I can see right here that this is unstable, and if there's something that's electron rich around it, it's going to react with it. In fact, it's a very violent reaction. This is a very unstable molecule. So Lewis dot structures help us understand some properties, the chemical properties of compounds, and that's why we do this. All right, so we can break the octet. That was the thing I was trying to show you here. So let's talk about exceptions, when the octet rule can be broke. Well, I'll start off with something when it cannot be broke. The second period elements, carbon, nitrogen, oxygen, and fluorine, they'll always obey the octet rule, which is nice. These are always going to follow the octet rule, and they are located on the second period. Okay, these are only on the second period. Make sure you have a periodic table in front of you when you're watching this, and pause the video as needed to kind of see if you can follow along. So now the second rule is the second period element boron often has fewer than 8 electrons around it. Around it, not them. My goodness. And voila, it says it now, not them. So it often has less than, and as we saw that because that's got 3 valence electrons and it's not very electronegative, and that's why it has often less than 8 electrons around it. So this boron is often electron deficient, and therefore things with boron that only has 6 valence electrons around the boron, these are very reactive compounds. The second period never exceeds the octet rule. In other words, these elements in the first or second period, the first period is just hydrogen and helium, they'll always have 2. Second period will only go up to 8. Boron can have less, but everything else will only go up to 8. It will never exceed the octet rule. Okay? Exceed. How can you exceed the octet rule? Let me give you an example of that. My goodness, this has really exceeded the octet rule, hasn't it, guys? Sulfur hexafluoride. Sulfur hexafluoride. Some elements exceed the octet rule. These elements are found in the third period and below. On your periodic table, identify sulfur, where the location of sulfur. Sulfur is in the third period, and these exceptions only, sulfur is right over here. Sulfur is in the third period, so we've got period 1, 2, and 3. Things that exceed the octet rule are only found in the third period or lower. This sulfur in this diagram here has 12 valence electrons around it. Remember, 8 is the ideal situation. 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's a lot of electrons around the sulfur. It's very, very much overloaded. So how does this happen? Well, if you recall from prior lessons, electron configurations, sulfur's electron configuration would end at 3s2, 3p, 1, 2, 3, 4, 3p4. So it'd end at 3s2, 3p4. It would look like this. 3s2 and 3p has 1, 2, 3, 4. Sulfur can add more than, when it's bonding, it can have more than 8 valence electrons, because even though there's nothing in it, there's a 3d orbital available. Go back to your electron configurations and diagrams lessons if this is confusing you. So there's a 3d orbital available. So what can happen here with the sulfur is these paired electrons here, the fluorine is very electronegative and it's trying to pair. It will naturally pair with these lone ones here, but the fluorine's so electronegative, and the 3d is still in the third shell, and although there's nothing in it, it exists. So an electron can slide out from the S into the D, and that one can go from the P to the D, and now what you have here is a whole lot of lone electrons that can be used to pair. So what happens in this situation is you've got 1, 2, 3, 4, 5, 6 pairs. 1, 2, 3, 4, 5, 6 pairing. So it's pairing like this because this empty d orbital is available. If you look at oxygen on your periodic table, oxygen is located right above sulfur. Oxygen is right here. And oxygen also has 6 valence electrons, but the thing is there's no such thing. See, oxygen stops at 2d4. 2p4. It's got 2s2 and 2p1, 2, 3, 4. It stops at 2p4. And when that's so this happens here, but oxygen, there is no such thing as a 2d. There is no extra orbitals for oxygen to slide extra electrons in there, and this is why oxygen cannot exceed the octet rule, and why things like sulfur can. So again, things that are on the third period or lower have empty d orbitals that can kind of move things around, and they can make some exceptions to the rule. If it's second period or higher, you will never exceed the octet rule, and this is the reason why. So now you should understand the fourth exception here. The third row and heavier, this is just in writing, this is just what I was talking about. The third row and heavier often satisfy the octet rule, but can exceed the octet rule by using their empty valence d orbitals. This is how they exceed, by having empty valence d orbitals. So valence, remember, is the outermost. When you're writing a Lewis dot structure, always try to satisfy the rule, the octet rule for the atoms first. If you can make it an octet, do so. Don't overload just because it's possible. It only overloads because there's no other option. If there's any option to fulfill an octet first, that's your first priority. Fulfill that octet. Then if you can't fulfill the octet, you can break the octet, but if you're going to do so, you place extra electrons on atoms that have available d orbitals. So they have to be third period or below. So you got to double check your periodic table, make sure that the third period or below, and then you can overload. So let's take an example of this. Phosphorus pentachloride. With phosphorus pentachloride, and I'm going to just do a textbook way of solving this, and then I'll do the connect the dots way of solving this. We have a phosphorus which has 5 valence electrons. Remember, you should double check your periodic table and pause as needed. And you've got 5 chlorines, and each chlorine has 7 valence electrons. So 5 chlorines, each one has 7. So we're going to multiply 5 times 7 is 35 plus 5, and now we have 40 valence electrons to play with. The second step, when you go textbook style, or the proper way that everyone explains it, is to connect everything. So since phosphorus was my first element listed in the molecule, that's going to be my center molecule, and I'm going to surround it with 5 chlorines. And so I've got 5 bonds, 1, 2, 3, 4, 5. If I've used 5 bonds, that's 10 electrons. Remember, each bond is 2 electrons in each, so I'm using 10 electrons here. I had 40, I have 30 left over, and I'm going to place the rest of those electrons, those 30 electrons, to fulfill the octet as best I can. Now, phosphorus is third period, so therefore it can exceed the octet, and in this situation it's exceeding the octet by 2. It's got 10 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But all the chlorines have 8. So this would be an example of that. Let's do this again with just the connect the dots method. I have, again, I'm doing phosphorus pentachloride. Phosphorus pentachloride. Phosphorus has 5, 1, 2, 3, 4, 5, and we've got 5 chlorines. I just draw them around, and each of those have 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so I've got my, I don't want this to be part of my things. I'm going to just kind of make it off to the sides here. So when I connect here, I'm connecting the dots. I connect the dots here, and it looks like a best situation would be phosphorus trichloride, but this is phosphorus pentachloride. There is some more. And so what I'll do is I stop here and I double check my periodic table. Can I make more connections with my phosphorus to these chlorines? Because it looks like I have to. So let's double check, make sure phosphorus is on the third period or heavier, and it is. It's on the third period. So I can overload this phosphorus. And so since I can overload this phosphorus, instead of being paired, let's think of them as separated. Now I'm overloading. And so now I can connect this one here, and I can connect this one here. So everything's connected, and I overloaded this phosphorus. Now the phosphorus has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 around it. And then if we write this clean, and I've got one over here, and I've got, looks like 2 on the bottom, another one on the bottom, and one over here. So I got all these chlorines. So that would be the way I would turn it in. Nice clean picture like that. Looks like a guy standing there doing jumping jacks or something. All right. Okay. So for the workshop, there's 10 examples here. In these examples, you will need to use the bank. You'll make deposits. You'll make withdrawals. You might make a deposit and withdrawal in the same problem. Hint, hint. Number 2 will be the first time you have to do that. You will have to make deposits and withdrawals all in the same problem, but you got to use up all those. Remember also in topic 6, we talked about ionic compounds and memorizing your polyatomic ions. So if you look at the first 5, if you have not memorized your polyatomic ions, you might be good at Lewis dot structures, but you're not going to be able to answer them. So you do need to study them. Go back to lesson 6 or topic 6 and review that if you're not comfortable with them yet. And there is a Quizlet linked on the topic 6 lesson on mrrast.com, mrrast.com. That will help you study for those polyatomics, just some extra practice there. So work these out. We'll go over the correct answers to all these in class. If you have any questions, make sure you ask, because it will start to get difficult if you don't ask. I love to help you out. Just let me know what I can do for you. Take care and good luck.